let's take something you already know about parabolas and abstract them to polynomials in general. I'm going to take, let's take parabola x squared minus 1. Let's take this one, and we know this factors. This is a difference of a perfect square. So we know this factors into x plus 1, x minus 1. That's one of the things you should be looking for. You should be able to recognize this difference of perfect squares when you see x squared minus 4 or minus 9, minus 16, blah blah blah. You recognize that as difference of perfect squares. So when you have a parabola, one of the things you can do is find out where it crosses the x-axis by setting this equal to 0. And when that happens, you get, if this equals 0, then either this equals 0 or this equals 0. So that means that either x plus 1 is 0, which means x equals minus 1, or x equals plus 1. So that means this parabola has zeros at 1 and minus 1. Well, a parabola, we can just think of it just as a regular polynomial. A polynomial of degree 2. So it has a degree 2. Remember we talked about degree and the coefficient out here? The coefficient out here is 1. So if it has a degree, even degree, and a positive coefficient, it goes off to infinity in both directions. We say as x goes to infinity, y goes to infinity. As x goes to minus infinity, this way, then y goes to infinity also. So we know it goes like that, and we know it's degree 2, so it has at most one turn. So now we also know it goes through this point and this point. So we can kind of put it all together and draw our parabola. And this technique works for every polynomial. Works for every polynomial. Sometimes it doesn't work out as nicely. But we'll pick ones that work out nicely. So that's the way you can look at this, and just by finding the zeros and knowing how it goes in infinity, you know it's going to look like this. It can only have one turning point, so it can't do anything else weird here. So let's abstract this to a little higher level. I do want to show you one other parabola. Let's see. Let me clear this one out. Let's try y equals x minus 1 squared. This is another parabola. If you multiply this out, you get x squared minus 2x plus 1. But here it's factored, so that helps you. If you set this equal to 0, when you're finding the zeros, just set it equal to 0. You know that this goes to infinity that way again. This goes to infinity that way. And there's a 0 when x equals 1. There's only 1. So there's a 0 right here. Well, as it's a parabola and it just goes there, you know it just touches right there. So that's the parabola you have. It has two zeros, but they're the same thing. What we do here, so this is an unusual 0. Instead of passing through the axis, it just touches. And in fact, whenever you have a 0, this power on the 0, so we really have two zeros of 1. So the 0, this 1 has a multiplicity. We say it has a multiplicity of 2. The previous zeros had a multiplicity of 1. This has a multiplicity of 2. And whenever it has an even multiplicity, it touches. touches the axis. Alright, if it has odd multiplicity, like 1 or 3, then it passes through the axis there. T-H-R-O-U-G-H, the axis. So the previous one had 2 of multiplicity of 1. They passed through the axis. Remember, I'll just throw it here to remind you. It went through 1 anyway. So if you had this red one is x squared minus 1, which ended up being x plus 1, x minus 1. These each had a multiplicity of 1. The multiplicity is this sort of power on the factor. Multiplicity of 1 they pass through. Multiplicity of 2, 4, 6 they touch. 1, 3, 5 they pass through. So it's another thing you can use to tell what's going on. In fact, let me give you a cubic equation, the simplest one. Y equals x cubed. So what happens when we set this equal to 0? Well, that's 0 when x equals 0. And it happens 3 times. So this has a multiplicity of 3. So this is a degree 3 equation. It has a positive coefficient, so we know it does this. And we know it goes through the point 0 and nowhere else. There's no other zeros. So it's a multiplicity of 3, so it passes through. And you see it kind of has to, because if it didn't, there's no way to connect up these 2 points. In fact, your book makes a point of using the intermediate value theorem, which is a very important theorem, but when we look at it, it seems kind of stupid at the level we... Intermediate value says if you're negative on one side, and you're positive on the other side, there must be a value at which it passes through the axis. It kind of makes sense. It doesn't seem very important. It turns out to be extremely important later on. But later on in other courses. That's called the intermediate value theorem. But I don't want you to remember that. It just says, well, it's very important. But not for us. Okay. X cubed only passes through 1 point. A multiplicity of 3 is at 0. So it does pass through. If it's odd, it passes through. If it even, it touches. That's about it. So let me take one more. Let's see. Let's come up with something fun. Y equals x plus 1. Y equals x minus 1. And x minus 3 squared. Alright, so here's a polynomial. It's a pretty big one. You're going to have an x squared times an x times an x. So this is going to be an x to the 4th polynomial. What's the coefficient on all those x's? These all have 1 as a coefficient. This one does get squared, so if it had a 2, it would end up being a 4. But the coefficient is 1, so even degree ones go off to infinity in the positive direction if they have a positive exponent. That's fine. But what kind of zeros does it have? Well, it has a 0 at x is minus 1. It has a 0 at x is positive 1. And a 0 of multiplicity 2 at x is positive 3. Alright, so it's multiplicity of 2, so we know it touches here, and it passes through here. So we have our, it has at most 3 turning points. It's degree 4, so you subtract 1 to get the number of turning points. So it does this. Just touches here. This is the multiplicity of 2. It's the x minus 3, 0. Again, we get these zeros by setting this equal to 0. Sometimes we'll have to factor these. Hopefully they'll be very easy to factor. This wouldn't be easy to factor, but we may give it to you in this form. So this is kind of what this one looks like. And you did this all without plotting points. You can, as always, plot points and see what you get. You could see what you get at 2. Let's see. 2 becomes 3 times 1. 2 minus 3 is 1. 1 squared of minus 1 is 1. You get like 2 up here. You can always plot points on these things. And your calculator, you can put this in very nicely and get this graph out. Okay, so we've added finding the zeros of polynomials. We've abstracted finding zeros from parabolas, and now we can use them to find zeros of polynomials. Okay, so we'll have a few problems on that. Pretty straightforward stuff.